Okay, so hopefully things are working fine. So welcome to next class where we'll be discussing the physics of ferromagnetism or the statistical physics of ferromagnetism. I'll start by reminding you what is the phenomena of ferromagnetism, then talk a bit in terms of try to give you the physical picture. Uh, and that's where we shall also differentiate from the phenomena of paramagnetism. And finally, we shall do some uh, mean field theory, and I shall tell you what mean field theory is. So that's how to solve the Hamiltonian, uh, the statistical physics Hamiltonian, uh, to get out the mean magnetization as a function of temperature. But we can't do it exactly and analytically. Well, we can do it in 1D and in 2D, but not in 3D. And hence we make use of some approximate methods called the mean field, and the approximate method is the Weiss mean field theory. So that's what this discussion is going to be about. Just to start with, I shall remind you that what is the phenomena of ferromagnetism. So things like iron show spontaneous magnetization or magnetic field. I mean, they have a finite magnetic moment in the absence of a magnetic field. So they have it spontaneously at suppose room temperature, but the magnetic moment uh, per unit volume, say, or whatever per I mean, you can normalize it in different ways. You can say magnetic moment of an entire sample, or you say magnetic moment of the sample per mole, magnetic moment per mole, or you can say magnetic moment per unit centimeter cube, say, or you can say, okay, let me calculate the average magnetic moment per atom or per lattice site. So whatever be you are normalizing with M0 here. Yeah, I mean, it can be of sample as well or normalized. So the measured magnetic moment uh, uh, compared to the magnetic moment at zero temperature. Of course, zero temperature cannot be reached, but I mean, suppose there is perfect ferromagnetic order. And what does ferromagnetic order mean? Well, we shall get to know in 10 minutes. So the magnetization, I mean, even if you didn't have a normalization, the maximum magnetic moment uh, at zero temperature would have a certain value, and it would nearly remain constant, but slowly, gradually, it will start decreasing. And at a certain temperature uh, called Tc, so this temperature scale is normalized by Tc. So if you multiply by Tc, it will have some value for iron. I think it's some 750, around 750 centigrade, uh, approximately. So at that value of temperature, the spontaneous magnetization will vanish, which means that the spontaneous magnetic moment in the absence of a magnetic field, its value will be uh, zero above a certain temperature. But below a certain temperature, there will be a spontaneous magnetic moment. And the question is, okay, I understand that different you have different atoms with spontaneous magnetic moments, but how come they all combine and they uh, basically support each other? They all point in the same direction in a magnetic sample, so that the entire sample shows a bulk magnetic behavior, right? So the, this is the experimental data. The solid line is the theoretical data, and this line with and these circles show the experimental data for nickel as measured by Weiss and whatever for in 1926. So such behavior of the magnetic moment in a sample was seen, and it gradually decreased in this manner. And the question is, uh, That's a bulk measurement. The question is, do we know what is happening microscopically? What could be the interaction between the magnetic moments such that we see such behavior, quantitatively match and explain the behavior. Moreover, what is also seen is for a different magnetic sample called the gadolinium metal, yeah, uh, above the Curie temperature, it showed 1 by chi showed linearly increasing uh, with temperature. 1 by chi is linearly increasing by temperature. Moreover, what you see here, that at a certain particular value of temperature, 1 by chi equal to 0, which is indicative that chi is nearly infinity. Of course, in a finite sample, you don't see exact infinity, but if you extrapolate the line, you would see that at 0 temperature, it has some whatever. I mean, so let's stick to this point. Uh, yeah. So here, it essentially, if you extrapolate at a finite value of temperature, the chi seems to go to infinity, so that 1 by chi is 0, and above that it increases linearly. Can we understand that? So these are the questions. These are observations which are seen. So these are thermodynamic observations, and the question is, can we make sense of such a sample in a statistical manner, in which by which we mean that can we describe the microscopic Hamiltonian, and then using statistical mechanics calculate the thermodynamic properties which we can match with the experiments. And if it matches various aspects, magnetism, behavior of magnetization with temperature, behavior of chi with temperature, and so on and so forth, chi being the susceptibility. uh, just to remind you, what is susceptibility? It is del m del b as b tends to 0, which means if you switch on a small magnetic field, b tending to 0, uh, how much is the change in magnetization, right? B tending to 0. So how does the sample respond to a small change in the magnetic field? It's a response function, because you're applying an external magnetic field and then looking at what the response of the system, what is the change in the magnetization of the system in response to an external magnetic field. So that is what is chi. So all these things should match, and then if they match, we say, okay, maybe this particular microscopic Hamiltonian is a relevant description of the system in question. Yes. So with that, let's proceed further the discussion. So this is the problem, and question is, what is the solution? What is the microscopic Hamiltonian? The other thing which we need to tell you, that when we are talking about magnetization, we are actually talking about a particular domain uh, inside a magnetic sample. So let me explain what I mean by that. When you have played with a magnet, I mean, I suppose an iron bar, at room temperature, you might have seen it to be, sometimes it's magnetized and sometimes it's not. And the reason it is not, that there are certain regions within the sample where you have magnetic moments pointing in different directions. And when you stroke it with another magnet, so that you align the net magnetic moments of different domains, so that on an average, they all point in the same direction, that's when the entire sample shows a finite magnetic moment. Now, if you heat it, or if you hit it hard against, say, the floor, right, then there will be, again, these domains might start pointing in different directions. Some are pointing up and some are pointing down, and so on and so forth. As a consequence, the whole sample as a whole does not show a net magnetic moment. But if you manage to break it down and looked within a domain, a certain region where on an average magnetic moments are pointing in the same direction. Now note the word, I use the word on an average, now, which means that even within this sample, you would see some of the magnetic moments pointing in the opposite direction. Mostly they are pointing in the same direction, but some of them might point in the other direction. It's similar to saying that in a paramagnetic sample, if you switch on a magnetic field, of course, a large number of them at reasonable temperatures, at relatively low temperatures, a large number of spins will be pointing in the direction of the magnetic field, but there will be a few magnetic moments which will take energy from a reservoir, from the thermal bath, and they can access local they can access higher energy levels. As a consequence, the microstate as a whole will have an energy corresponding uh, higher energy microstate. So, right? But I mean, even in a paramagnetic sample, if all spins were pointing in the B direction, the direction of B, that would be the lowest energy microstate. But you can have only one microstate like that, right? Where all spins are pointing up. But what the system will do, especially if n is large, is some of the spins can take some energy, absorb some energy from the surroundings, from the bath, and access some higher energy levels where the spins can flip. And as a consequence, any of these spins can flip, and that can give rise to a large number of microstates, as a consequence of which the free energy, which is F equal to U minus Ts. So U, yes, you want to decrease, but then if this is depending what temperature, if the system can take some energy and access large amount of microstates such that S becomes, averages becomes large, then F equal to U minus Ts. The minus Ts can also contribute and can minimize the free energy, right? Similarly, here, for whatever reasons, even in the absence of a magnetic field, large number of magnetic moments point in the same direction, but it is possible that some of these spins can take some energy from the reservoir and point in the opposite direction. And that's the reason why I said that suppose within a particular domain, on an average, suppose the most of the magnetic moments are pointing in the up direction, and in this domain, it's pointing in some other direction. Let's say, I mean, just as an example, right? Here also again on the average, and the domain wall or the domain boundary are these list of atoms or grains. I mean, there are regions, lines along which atoms sit, where it doesn't know, I mean, whether it wants to align in this direction or in that direction, right? And if you can remove the, so these are lines of some sense disorder or something like that, and if you remove the domain boundaries, of course the entire sample can point in the same direction on an average, and because some spins will always be trying to point in the other direction at any finite temperature. Of course, if thermal fluctuation is zero, in that ideal condition where T equal to zero, then of course you won't have that. So the point I want to make, that when we discuss ferromagnetism, yeah, we are discussing the physics of only one domain. So we are looking here at T equal to very close to zero. Most of the spins are pointing in the same direction, where there's a very high magnetic moment, as we saw in this picture. At T equal to zero, there's a very high magnetic moment, but as we increase temperature, the number of magnetic moment of the samples slowly, gradually decreases, and here slowly it goes down to zero. And the question is, how can we understand that? And the way we understand that is through the so-called Ising model. So Ising model is what we will discuss. So that's a model Hamiltonian. It was proposed by Lenz in 1920, and he gave it to his PhD student Ising. I don't remember his first name, but just look up Wiki. And what he calculated is, so we're going to discuss that model, Hamiltonian Ising model, and he saw that he didn't see any magnetism. He could solve it in 1D, and any magnetic order, any finite magnetism, magnetic moment of the sample in 1D immediately disappears as soon as there is a any finite temperature, any small thermal fluctuation, find very small temperature, you'll see that there's no net magnetic moment uh, which is obtained, which means that the system does not show magnetism. What does it mean that it does not show magnetism? That only at t equal to 0, within a certain domain, we are always talking within a certain domain, all the magnetic moments point in the same direction, but any finite temperature, there is no net magnetization of the sample as per the theory, as per the Ising model, as solved in 1D. So he thought that is not a very useful model, and that does not describe ferromagnetism, because as you saw, as in the experimental data, you do see finite values of magnetism, uh, magnetic moments persisting till you reach the Curie temperature. Only above Curie temperature, you see there is no net magnetic moment. And the Ising model couldn't or doesn't show that in 1D. And so he mistakenly thought that that's a Hamiltonian which does not describe ferromagnetism, but he was wrong. So basically, after that, the war came in, and he had to run from Germany. So he was a Jew, and he had to run from there to Luxembourg, and Luxembourg was taken over by Germany. And then, cutting a longer story short, he reached US sometime in 47, and only in 1949, Wikipedia knowledge, did he realize that the model proposed by Lenz and solved by Ising actually had been in meanwhile solved by Onsager, and there had been a lot of work done, and Onsager could solve it exactly in 2D, and there were many other approximate methods, including the Weiss approximate method, which was proposed, and it actually showed ferromagnetism, finite magnetic moment at finite temperatures in 2D and 3D. In 3D, you do approximate methods or computer simulations, and it was a valid, simple model for showing ferromagnetic order. Right? We'll talk about this later, but let's get into what is the Ising model. It's named the Ising model, and if one understands Ising model, one can understand a lot of physics, but that way. So what we think considers, so what Ising considered was just a 1D lattice. Okay. So basically, there's spins sitting along a line, but in general, I mean, suppose this is a lattice, and you have spins sitting at different points along the lattice, right? And at each point, you have a magnetic moment which can either point up or down. Yeah. And so each spin, if it's a 2D lattice, is surrounded by 4 nearest neighbors. So the nearest neighbors of this spin is this one, this one, this one, and this one. These are the nearest neighbors. And these diagonal ones, or with respect to this, are the next nearest neighbors. So in the Ising model, you are, in the simplest version, you are considering interaction. So this spin is interacting with only its nearest neighbors. That means these 4, 1, 2, 3, 4. Similarly, this one is interacting with this, and this, and so on and so forth. So this one is interacting, of course, whatever spin is sitting here and here, this and so on and so forth, right? But of course, you can have different lattice arrangements. You can also have a triangular lattice, in which case this spin will interact with this one, this one, this one, and yeah, this and this. So there are 6 neighbors. Similarly, you will have 6 neighbors if you have a lattice in 3D, because you will up. So suppose this is a spin, it will have a neighbor in this direction, right and left, and then into the plane. I mean, it's like here and here. So 6 neighbors again, right? So the number of neighbors will be 2 in 1D, will be 4 in 2D. If you have a, if you have just, I mean, if in 1D, if you have one neighbor on the left and one neighbor on the right, if you have a square lattice, then you will have 4 neighbors. And if you have a cubic lattice, you can have uh, 6 neighbors. But of course, even in 2D, you can have 6 neighbors if you have a triangular lattice, right? So what it says is, if there are 2 magnetic moments sitting on a lattice, the question is, how can you get spontaneous magnetic moment at a macroscopic level? And the simplest model is the Ising model, which says that if a particular magnetic moment, suppose this one, is pointing in the up direction, then if its nearest neighbor, this one, is pointing in the same direction, so there is a Hamiltonian, so there's some interaction which basically tries to minimize energy if 2 spins are pointing in the same direction, which means if this spin and this spin are pointing in the same direction, then in terms of the Hamiltonian, the exchange interaction, so it's called the exchange interaction, is such that these 2 spins pointing in the same direction will have an energy minus g. Minus g is a unit of energy, right? They will have energy. And the energy cost will be minus, negative. So energy will be minimized. Free energy will be minimized. I mean, of course, free energy is U minus Ts. On the other hand, if 2 spins were pointing in the opposite direction, suppose this and this, that would cost energy. That would cost energy, a cost of plus G. Yeah. So the way you can write is that suppose Si is the, or suppose this spin is Sg, then you take a dot product, you do a dot of all its neighbors. So if Si is in the same direction, suppose Sj is positive and Si is in the same direction, so then positive into positive, and it would give a minus G energy cost. The next one, suppose this one, so if Sj is positive, in this case, Si runs from runs on nearest neighbor. So this one is negative. So this quantity Si dot Sj is negative, and minus J into a negative quantity is positive. So there will be a positive energy cost. And similarly here, there will be a positive energy cost and a positive energy cost, right? So that's how. So that's the interaction of one spin with its 4 neighbors. But then, of course, if you have if there are n spins in the lattice, then I can run from 1 to n. For each value of I, sorry. So what I should have done is, basically the way I have written it is, I runs from I to 1 to n, which is over all the spins in the lattice, and j is over the nearest, sum over the nearest neighbors. So Si is this one, if you like, and Sj are the 4 nearest neighbors of each spin. So to choose I equal to, suppose this is the 40th spin, and j runs over 1, 2, 3, 4. Then you go I equal to 41. Suppose this is the 41st spin. Then you sum over its 4 neighbors, and so on and so forth. And then you go to this one, I equal to 42nd, suppose, and then you sum over its nearest neighbors, and so on and so forth. So the entire Hamiltonian of the sample is I runs from 1 to n in that sense, and j is the nearest neighbors of each of spin I, and thereby this Hamiltonian describes the interaction of each spin in the lattice with its nearest neighbors. Now, for the entire sample, of course, the Hamiltonian will have many other terms which will create the lattice. There might be interaction between electrons and the lattice. There can be interaction between electrons and the nucleus. There can be interaction between different other atoms, but those will be additional terms. The part which we are focusing on right now is only the magnetic interaction. The question is, if there's a magnetic moment and it interacts with its neighboring magnetic moments, can it at a finite temperature make a large number of spins point in the same direction at a finite temperature such that the entire sample within a domain shows a finite magnetic moment? Does it do it, and does it do it in the way we see the experimental data? So that is the question we are asking, right? So we are interested in only the magnetic interaction of the sample. In addition, there will be many other terms in the Hamiltonian, in the full Hamiltonian, but those, but as long we are interested only in the magnetic interaction and interested to calculate only the magnetic properties, when we calculate it, these other terms will be there in the numerator when we are calculating the probability of occupying a certain state, where we are interested in talking about a magnetic certain state only. And of course other terms will be there, but they will be basically static, and so when calculating averages they shall cancel from the numerator and the denominator, right? So this is the big picture I want you to have. Now this J is called the so by the way, this is Rife section 10.7. This J is called the exchange interaction term. Now for the so now the thing to remind yourself, I mean the thing to tell yourself is basically that this quantity J can be calculated from overlap of wave functions. Quantum mechanically, if there's a wave function and there's so of a magnetic sample, how much does it overlap with its neighbors, and so on and so forth. And so one can have a microscopic calculation which gives explicitly the value of J, depending upon how much overlap there is and what magnetic sample you have. But what we are going to do is not do the microscopics, we shall assume, and somebody else has done and calculated the value of J, and having known the value of J, can we calculate the magnetization of the entire sample, the average magnetic moment of the entire sample, and look at it as a function of temperature. On the other hand, when you are really looking at a new sample, you might not know all the microscopic interactions. And if this model gives the right thermodynamic behavior and you can match it, and you don't know the value of G, you have in hand as an experimentalist, you have them in value. Only the magnetization is a function of temperature. And if suppose that magnetization curve is correctly described by this Hamiltonian or the statistical mechanics using this Hamiltonian, right, where a priori you do not know the value of G, and if you can calculate a Curie temperature from the statistical physics and you can measure it experimentally, in that case, microscopically, you might not know experimentally what is the interaction, but assuming this Hamiltonian, and suppose this Hamiltonian is a right description of the phenomena of magnetization phenomena in nature, and you know the Curie temperature, then you know that this Hamiltonian is a correct description of the interactions, atomistic interactions, and since you know Curie temperature, you can get out the value, the strength of interaction. How does that happen? I think once I do the calculation, we can discuss this further and you will be able to understand this better. The other point, the other thing to write before actually going down into the calculation, in Rife, the Hamiltonian is written over H equal to minus 2j Ising. Ising is Is for the Ising Hamiltonian, which is the same as the exchange Hamiltonian. Sum over all spins. I runs from 1 to n, and j is the nearest neighbors. Now, if you do that, I want to tell you that you actually overcount. Okay, so let me tell you how. So when you take this spin and say you sum over its 4 neighbors, right? Then the interaction is this. So you're going to calculate the interaction of this spin with this spin, right? And that is minus j interaction. Similarly, right? And for this spin, you calculate the interaction over this neighbor, this neighbor, this neighbor, and this neighbor. But again, when you come here, and if I is this spin, so this was suppose 40th and this is 41st, and then you again calculate its interaction with all its neighbors, right? So then this spin, again you consider the interaction of this spin with this spin, right? But you have already considered it once. The interaction is minus j. Now you don't do it, you calculate this with this, and that's minus j. And again, you take this and you calculate its neighbor this, that's minus 2j. So you are overcounting it. The interaction between two spins is only once, right? It should be counted only once, right? So and it's j, that is the interaction. So what you could do, that if I runs from all spins, you have to ensure that there is no double counting, right? So that you basically ensure that I runs from 1 to n, but when it's going over nearest neighbors, you ensure that there's no double counting. You have to ensure that while calculating the energy or energy of interaction. Alternatively, the convention that Rife uses is the Hamiltonian is written by minus 2j Ising, and SI and SG can take plus half values only. So the consequence is, so you do double count in the Rife convention. Okay, so this can take half and this can take half value. Suppose these two are pointing in the same direction. So this is half into half, that's 1/4, right? And then it's into minus 2JIS. So that's minus J, half J is the interaction between these two spins. But once you double count, because you're taking I and then average over all its neighbors. So again, you go here and average over all its neighbors. So you have to double counting, but finally, so this is half into half. So when you count once, and that gives you minus half of j, minus half of j. And when you do the double count, you get another minus half of j, right? So correct interaction value between this and this is, suppose minus j is the interaction. If you write in this convention, that is taken care of, even if you double count, and it will have some advantage, as you shall see. The other way to write it is take S to be +1 and -1. I runs over all spins, and J runs over nearest neighbors, but you have to ensure that you don't double count. Now, this ensuring that you double count can become a bit messy, right? So you have to be a bit careful about that aspect. So whereas in this convention, double count will give you the right energy, right? And the other thing I need to tell you is basically we are talking about spin, uh, right? So up spin and down spin, where the spin can take plus and minus half values. So in Ising model, the spins can point only up and down. I mean, so it can take only plus one value or minus one value, or equivalently plus half value and minus half value. There are only two states possible. Of course, you can have other magnetic moments where more states are possible, or it can take continuous values, but those are not the Ising model. In Ising model, that's the simplest model. You allow only up and down, whether you call them plus one or minus one, or plus mu, magnetic moment mu, minus mu, or half minus half, it really doesn't matter. And finally, the point is the energy of interaction has to be J Ising equal to J exchange. And if you are really talking about magnetic moment, you have to multiply each spin by the suitable Bohr magneton and the what is it called, Landigi factor, and so on and so forth. So all those aspects are absorbed within this JIS. Okay. So we are talking about spins plus one and minus one, but you should remember that they're actually spin half particles, and it has, since we're talking about magnetic interaction, there is also the spin multiplied by the Bohr magneton and the Landigi factor will give you the magnetic moment, and that's what you are actually calculating, right? You are actually calculating what is the total magnetic moment. But all those things are absorbed within GIS, and then we can keep talking about the spin. You can just keep talking about the spin, whether we call it, plus half or minus half, or one and plus one. That would just change this quantity. Okay. So finally, what you have, that the Hamiltonian for a particular spin I, is minus g into the magnetic moment. So minus g into mu zero is basically the magnetic moment, into the spin quantum number, into an externally applied magnetic field in case there is any. But in a ferromagnetic sample, even in the absence of B, you should show spontaneous magnetization. And if you have an extra B, that can add to the magnetic moment. Minus 2J Ising SIZ, like suppose this is broken, you are applying a magnetic field and a spin can point in the Z direction. So this is the spin of I, and sum over all neighbors. And since Hamiltonian of the entire sample is sum over I, then there will be a double summation. Here you are writing the interaction of one spin with its neighbors, and if there is a magnetic field. And the point is that this cannot be solved in 3D as of today, and 2D it can be solved exactly, was done by Onsager 20 years after the Ising model was first proposed by Lenz actually. But that's an extremely complex mathematical calculation, which will be done in the StatMech 2. And what we will do is do the so-called mean field theory. And the question is, what is the mean field theory? So let me take a break and continue in the next class.